Hi students. So today we start lecture 9 in the Fortran tutorial series. Today I am going to discuss the complex step method. So this is a numerical method to calculate derivatives, and we are going to briefly describe this method, and then I am going to write a Fortran program to implement this method. The method is very good. It's much superior to the classical finite difference method. I am Dr. Ganguly. So let's just start with the forward finite difference formula most of us are familiar with. I've also discussed this in my previous lecture. So essentially this comes from the definition of the derivative. So the derivative as defined as df by dx is approximately equal to f x plus h minus fx by h. And here h is a small number, typically a very small number, like it could be 10 to the power minus 4, it could be 10 to the power minus 8 or something like that. Now, of course, you know from the mathematical definition of the derivative that this is the definition in the limit that h tends to 0. So we are making use of the basic definition of the derivative here. Now, the fact is that h should be a small number, and what's going to happen is that if h is very small, then fx plus h is almost going to be equal to fx. So essentially you are going to subtract two numbers which are very similar, and with that what's going to happen is that you are going to have a loss of accuracy in the computational arithmetic, and that's something you typically do not want to do. So on one hand you should make h as small as possible, but the problem is computers use finite precision math, and therefore h is limited in terms of how small it could be. Now the complex step method actually solves this problem. It avoids the problem of trying to subtract two small numbers. So let's look at that method. Now before we start this method, I will just recap on some concepts which you probably studied in your high school or in college. And these concepts are the concepts involving the Cauchy Riemann equations, and also something which is known as the analytic function. So these are essentially functions of complex numbers which are differentiable. So let's take a simple example to illustrate this concept and review this basic mathematics. So let's say there is a function fz is z square, and we use z here as a complex number which we can write as x plus iy. Now if I was to expand this complex number out, so I could write it as a function of two variables fxy, and so that would be x plus iy square. That would become x square plus 2ixy minus y square. Remember, the I square y square term becomes minus y square because I square is minus 1. So now I can express this in the form u plus iv. So u would be the real part and v would be the coefficient of I, that is the imaginary part of this complex number. So if we do that, then we are going to get u is x square minus y square. That's from this equation here, the real part, and v is going to be 2xy. That's the coefficient of I here. So we have values for u and v, and then we invoke the Cauchy Riemann equation. So these equations tell you that du by dx is dv by dy, and du by dy is minus dv by dx if you have a function fz defined as u plus iv. So we can now plug in these values and check out these partial derivatives. So we remember that if you were to differentiate u with respect to x, you would have 2x on this side, and v with respect to y, you would have 2x again. Remember, when you take partial derivatives, what happens is that you treat the particular thing you are differentiating with as the variable. So in case du by dx, you consider x as the variable with respect to which you differentiate, and the second variable y becomes a constant. So that's how you get these partial derivatives. So here, for example, du by dy would become negative 2y, and again dv by dx would become negative 2y here. So Cauchy Riemann equations are satisfied. Now typically with most polynomials, most well-behaved functions which we typically encounter in calculus type of problems, these kind of equations would be satisfied, and in general we can proceed with this method in most cases. Now Of course, if you are having problems where you have discontinuities in your function and so on, you may want to use some of the stochastic methods. You may not want to use any gradient based method then, for example, if you are doing optimization. So let's now try to derive the formula for the complex step derivative. So let's start with the function f is u plus iv, and we also know that z is x plus iy. So here f is a function of z, u is a function of z, v is a function of z, or we can say f is a function of xy, u is a function of xy, and v is a function of xy. Now I immediately write down the two Cauchy Reimann equations, and from this I can say that du by dx, because it's equal to dv by dy, I can write in this form. So this is essentially using the definition of the derivative. So I am taking v and I am perturbing y by some h, and here I have x plus iy here. So remember that v is a function of z, which means v is a function of x plus iy, and so the perturbation is here. So this is nothing but this part of the Cauchy Reimann equation written out in this nomenclature here. Also, the fact is that now x, y, h are all real. So the I is here, that corresponds to the complex part, but whatever is inside these brackets, for example, x, y, h, they are all real numbers. Now let's look at the actual case which we deal with in most problems. We deal with real functions of real variables. So let's say if we have a real function, then of course y would be 0 in z is x plus iy. Also, if we have the function fx is ux plus I vx, then this is going to be simply equal to ux because vx is going to be 0. So these two particular things which I have put in red, these ensure that you have a real function of a real variable. Now of course if f is x plus ih, then we will have to write it like this. And now let's go back to the equation I looked at in the previous slide, that is the definition of du by dx. And then what we do is we invoke some of these conditions. So we can clearly see that since y is 0, this term would become 0 here. Then we would be left with only vx, and vx is also 0. So this term would essentially vanish completely. Now of course, in this equation here or this term here, y would be 0. So I would be left with Vx plus IH. So that's the term here, Vx plus IH divided by H. And then I can write this expression as simply the imaginary part of f x plus IH by H, because if you look at this equation here involving fx plus IH, the imaginary part is the coefficient of this I here, and that would be Vx plus IH, that's this term here. So this is the equation which I get, and now this equation is going to give me the complex step derivative. So let's again write down this equation here in terms of limit, and then of course if we are going to do a numerical method, we are going to have to choose a very small value of h, and then we can write that df by dx is approximately equal to the imaginary part of f x plus ih divided by h. So this is the formula, and you can see in this formula that subtractive cancellations are no longer taking place, which are there in the forward finite difference formula, in the central finite difference formula, and so on. Now sometimes people find that way of derivation quite difficult to understand, so there is one more derivation, and let us take a look at that. Now we are going to use the fact that analytic functions have convergent Taylor series. So therefore I can expand fx plus ih in the form of a Taylor series. So I would get fx plus ih f dash x minus h square f double dash x by factorial 2 minus ih cube f triple dash x by factorial 3 plus so on. Now remember here, whenever you would have the I square h square term, the I square would give you the negative 1. So that's why some of these negative signs come out here and there. Now the next thing we do is that from this equation we take only the imaginary part. So I write im f x plus ih, and then that would simply become this part here, that is h f dash x. I would have this part here, so that would give me h cube f triple dash x by factorial 3, and many more terms may be out there. Now let's just keep in mind these three terms. We will ignore those terms because they are h 5 and so on, they are really small, because remember h is going to be small in this entire math problem, and therefore we can then write f dash x as im f x plus ih by h. So I essentially divide this completely by h, and I can write this expression out here. So this expression tells me several things. It tells me that if I have small h, that would essentially keep reducing the these terms out there, and so the equality in terms of f dash x and the im f x plus ih by h would be very much valid as h becomes smaller and smaller. So now let's try to write a Fortran program for this. So we are going to call this the complex step derivative. We are going to label it as CST. So what I do here, I say there is a complex function f, and I give h as a small number 1 e to the power 7 and or e to the power negative 7. Then I say x is 1, so this is the value at which I want to calculate the derivative. So the complex step derivative is this expression, which is the translation of this expression here in red. So you can see here I have taken the imaginary part of f, where f is a complex number having x and h as the real part and the imaginary part, and then I divide that entire thing by h. So I'm using two functions which are built into Fortran here, the complex function and the a imag function, and then I simply print out fdx and csd. Fd I will define in the next slide, that is the actual derivative value, and then also I have CST which I have calculated here. Now the function f of z, this has to be calculated. So f and z are both complex numbers, and I write f as simply this function here. So remember, f I am using as 3 to the power z minus z to the power 9. Now this is complex because remember that z is x plus ih. That's what's coming in from this complex value here. So this is returning this complex function back here. Now, of course, I have the function which I use for comparison, that is fd. Fd is nothing but the derivative. So I can differentiate this particular function, and I get 3x log 3 minus 9x to the power 8. And so this is 3 to the power x into log of 3 minus 9 into x to the power 8. Remember, double star is exponentiation in Fortran. Now let's take this and put it in the compiler, and I have put it here. Remember, h is 1e minus 7, and in this particular case we have coded in the complex step derivative. Very simple code. The two functions are there. One function is calculating the function itself as a complex number, and the second is calculating the derivative of the function for comparison, and the complex step derivative is coded in here, which is essentially the translation of this math into Fortran. And you can see here that the exact and the CST are comparing very well. In fact, they are comparing exactly as far as the decimal places here are concerned. Now, just to compare with something we have done before in one of our previous lectures, I think in the previous lecture, if we were to use the forward finite difference formula, that is this formula given here, then we would not get a good match here, even though we are using h is 1 e to the power minus 7, because of course you know there is round off, because x plus h is very close to x. So f x plus h is also pretty close to f of x. So you are essentially ending up subtracting two numbers, and that's not something which is generally good in numerical mathematics. Now, just to see what happens as h varies, let us put a do loop on h, which I have put here, and then I have printed out the different derivatives at different values of h here. So you can see h is very small here, and then h becomes, or rather h is pretty large here, and then h becomes much smaller here. So in this case, of course, you see there is the exact derivative, the finite difference derivative slowly starts becoming better, but if you make h too small, it essentially becomes 0, because I'm using single precision math, and there is essentially no difference between f x plus h and f of x. So the difference between them is simply 0 as far as 8 decimal places are concerned. But the CST is much more robust, that is the complex step, and complex step in fact not only converges faster, but it is very good at low values of h also. So certainly this is a nice method. You can also see here that I had to define the function again as a f real function, because in the case of the complex step derivative, what's happening is that I'm using a complex function here for that particular process, but for the forward finite difference I use the real function value. So there is of course some complexity in terms of using complex numbers. You may have to have changes made in your code in case you are using a code out there, but certainly if you are beginning something new, you want to use numerical computation for derivatives, then the complex step method may be very useful. So let me give you some homework problems. Generally, there is a phrase that the difficult problems are for the students. So I will say that you can write a program using double precision math to calculate the complex step derivative. Remember that in Fortran, what happens, the functions themselves may change if you use double precision math. So the complex function may not be working anymore. You have to use some d-complex function and so on. So you can check all those things out in Google and you will find a plethora of information on double precision complex math, which you can use here. Now, one more thing you can do is you can check what happens with the central finite difference derivative. So remember, the central finite difference derivative is given by this formula, that is df by dx is approximately equal to fx plus h minus fx minus h by 2h. So if you use this formula, you get somewhat better derivatives, and you can compare that with the complex step derivative. Again, the complex step is going to work out better. So today we used Fortran and we used this exercise or this tutorial to teach a particular concept, which was the complex step derivative. You know that numerical derivatives are very important in computational fluid dynamics, that is CFD, in computational structural dynamics, I would say computational mechanics and science in general. And also they are extremely important in optimization whenever you are using gradient based methods. So remember, gradients are nothing but derivatives, and these are all the partial derivatives out there, and a huge amount of time is actually consumed in trying to get this derivative information. Not only when you are doing optimization, you may be doing anything to do with problems where derivatives are required, and there are numerous problems like that involving solution of partial differential equations, for example, and also in numerical computation.